What's up, everybody? Welcome to the third lecture of trig. Today we're going to be talking about triangles. Go figure, right? Trig triangles. In particular, today we're talking about section 1.3. To start off with, let's talk about the anatomy of a triangle. When talking about a right-hand triangle, so a triangle where one of the angles is 90 degrees. We say that the leg opposite of the 90 degrees is going to be the hypotenuse. And when we choose from there a particular angle other than that 90 degrees to talk about, so let's say this angle here, we say that the leg touching it is the adjacent leg, and the leg opposite of it is the opposite leg. Go figure. Now it's using these titles of the legs that we redefine all of our cosine functions. In particular, I meant to say all of our trig functions. In particular, cosine is equal to the adjacent over the hypotenuse. So we take the length of the adjacent leg and we divide it by the length of the hypotenuse. The sine of that angle is going to be the length of the opposite leg divided by the hypotenuse. And the tangent of that angle is going to be the length of the opposite leg divided by the length of the adjacent leg. And from here, secant, cosecant, cotangent, we can define it in the previous way. Now, having said that, I want us to take a moment to look at tangent. Because tangent is equal to the opposite over the adjacent let's say we wanted to multiply it by 1. Won't change anything, right? It'll still be opposite over adjacent. Let's multiply it by 1. Now we can redefine that 1 as being equal to the hypotenuse, the length of the hypotenuse, divided by the length of the hypotenuse. When we do that, we get the opposite over the adjacent times the hypotenuse over the hypotenuse well, we can rewrite these fractions in particular we can rewrite them as the opposite over the hypotenuse and the hypotenuse over the adjacent. But now we can rewrite these. We can say this is sine of our angle and this is 1 over cosine. Which we can now rewrite as sine of our angle over cosine of our angle. So not only can we redefine secant, cosecant, and cotangent in the usual way, we can do the same thing with tangent. We can say, all right, cool. Tangent isn't just the opposite over the adjacent. It can be rewritten as the sine of the angle divided by the cosine of the angle. Having said that, let's move on. Now, before we tackle this first example, I really quickly want to touch on what we already know to be the Pythagorean theorem. The Pythagorean theorem states that given a right triangle, the length of the hypotenuse squared is going to be equal to the length of the adjacent squared plus the length of the opposite squared, as we have written here. Having said that, let's tackle this first example. Now, this first example, some of you might recognize from the notes. If you do, I'm going to caution you to be very careful tackling this problem. I wrote it a little bit different. In the notes, everything we're solving for is in relations to theta. On the board here, what we're about to solve is going to be in relations to beta. So just FYI, all throughout this class, we're going to be using a lot of Greek notation. So if you're not used to Greek letters, about to learn. So having said that, first thing we're going to want to do, if we want to find cosine, sine, and tangent of beta, the first thing we're going to want to do is find the length of the hypotenuse. Well, luckily, we've been provided with the length of our adjacent side and our opposite side. So we know that the hypotenuse is going to be the square root of 4 squared, that's our adjacent, plus 3 squared, that's our opposite. So the square root of 25, or just 5. So now we have what we need to tackle this problem, right? Now we can say, all right, I don't know what beta is. I have no clue what that angle is. But based on the information provided, I can still figure out what cosine of beta is. Cosine of beta is going to be the adjacent side divided by 5. So 4 divided by 5. Sine is going to be the opposite divided by 5. So 3 divided by 5. Excuse me. And for the tangent, it's going to be the opposite divided by the adjacent. So 3 divided by 4. From here we can find secant, cotangent, etc. Cool, let's move on. Now before tackling example 2, we should really quickly look at this idea of the sum of the angles. All we're saying with the sum of the angles is that for any triangle, you're going to take and add all of those sums, those three angles together. You're going to take alpha, beta, and gamma, add them up. Every time you're going to get 180 or pi radians. Having said that, let's look at example 2. In example 2, what we're trying to do is find the cotangent of 45 degrees. Well, because our trig functions are defined on right angle triangles, we can go ahead and start writing out this triangle a little bit. We know at least one of the angles is 45 degrees, and one of the angles is 90. Well, that means, based on this sum of the angles rule, that the remaining angle must be 45 degrees. Now, think about this for a second. We've got two angles that are identical. So that means the length of their opposite sides have to also be identical. So why don't we just go ahead and say, let the lengths be 1. Why not? So we're going to say this length is a length of 1, and this length is a length of 1. Well, if that's the case, given that this side, this leg, is opposite our right angle, it must be our hypotenuse. So let's write that in, hypotenuse. And it must have a length of 1 squared plus 1 squared, the square root of that, right? So let's write it out. Hypotenuse is equal to the square root of 1 squared plus 1 squared, which is the square root of 2. All right, so we know a little bit about this triangle now. Now let's work on this cotangent. Well, we know that cotangent is equal to 1 over tangent. And we know tangent is equal to sine over cosine, so we can rewrite cotangent as cosine of 45 degrees over sine of 45 degrees. But we know cosine is equal to 1 over the square root of 2. And we know sine is equal to 1 over the square root of 2. So all of this is going to come out to be just 1. Now some of you may have noticed right away that I had made this a little bit more difficult than what it needed to be. We could have said, all right, since that's 1 over tangent, this is going to be the adjacent over the hypotenuse. But I wanted to expand it out a little bit more than what was needed. And the reason why I wanted to do that is just to show that cosine is equal to 1 over square root of 2, and sine is equal to 1 over square root of 2. And the way we were able to solve this problem is all by using this sum of the angles rules. And then from there we said, all right, since those angles must be the same, the length of the corresponding sides must be the same. So now I'm able to get the hypotenuse and do the rest of the math. Cool, let's look at another example. And before we move on to another example, I really quickly want to talk about the Pythagorean identities. In general, there are 3 different Pythagorean identities that we should know. Having said that, we can memorize just this one and derive the other 2, and I'm going to show you how to do that. But all the Pythagorean identities are really telling us is that no matter what the angle is, the sum of cosine squared plus sine squared will always be 1. Now, having said that, how do we derive the other two? Well, to start off with, let's rewrite what we've got. We've got cosine squared theta plus sine squared theta is equal to 1. Now, if I divide both sides by cosine, so cosine squared, divide this by cosine squared, what we're going to have is cosine squared theta divided by cosine squared theta plus sine squared theta divided by cosine squared theta is equal to 1 over cosine squared theta. Well, we can see really quickly that this reduces to 1. 1 plus. Now, because both of these terms are numerator and our denominator are both squared, we can go ahead and pull the square outside. We'll have sine theta over cosine theta, the quantity squared, is equal to 1 over cosine squared theta. Now you might recognize this is going to give us tangent. So we can rewrite all of this now as 1 plus tangent squared theta equal to, well, 1 over cosine squared theta. That's going to be 1, or secant squared, right? Secant squared theta. So we just derived our first of the two identities. By dividing everything by cosine squared, we can show that cosine squared plus sine squared equal to 1 leads to 1 plus tangent squared theta equal to secant squared theta. Now let's go the other route. Instead of dividing by cosine, let's divide by sine now. So we're going to multiply by 1 over sine squared theta. Over here we're going to have 1 over sine squared theta. And together we're going to find that this comes out to be cosine squared theta over sine squared theta plus sine squared theta over sine squared theta. And all of this is equal to 1 over sine squared theta. Now, same trick as before. Notice that this becomes 1. And cosine squared over sine squared Or we can pull that square out and rewrite it as cosine theta over sine theta, the quantity squared. All of this equal to 1 over sine squared theta, or cosecant squared theta. Now you might notice here, this is equivalent to cotangent. So what we got is cotangent squared theta plus 1 is equal to cosecant squared theta. And this is our other identity. We'll go ahead and write it down. Cotangent squared theta plus 1 is equal to cosecant squared theta. And those are our Pythagorean identities. Let's use them now. To solve this final example, using only the fact that sine of theta is equal to 3 over 5, we want to find cotangent of theta. And then, assuming that our hypotenuse is 1, we want to find out what the length of our adjacent leg is. So how are we going to start this? Well, we can start by saying, all right, I know that 1 plus cotangent squared of theta is equal to cosecant squared of theta. And I know that cosecant of theta is equal to 1 over sine of theta. And I know sine of theta is 3 over 5. So altogether, this tells me that cosecant of theta is equal to 5 over 3. So now I can throw that into our first equation, right? Now I can throw that into our identity up top. Remember, this comes from the Pythagorean identities. Throwing that in, we get 1 plus cotangent squared of theta is equal to 5 over 3 squared. So let's go ahead and calculate that fraction. We've got 1 plus cotangent squared of theta is equal to 25 over 9. Now we can subtract the 1 from both sides. And we can rewrite it as 9 over 9. So when we do that, we're going to find cotangent squared of theta is equal to 25 over 9 minus 9 over 9. Subtracting everything, we find that cotangent squared is equal to 16 over 9 taking now the square root of both sides, we get that cotangent of theta is equal to the square root of 16 over 9, or cotangent of theta is equal to 4 over 3. Cool. So cotangent is equal to 4 over 3. But that still leaves this last problem. How are we going to find this adjacent length? Well, we could use the Pythagorean theorem. Or we could use what we just found. Cotangent theta is equal to 4 over 3. I say let's use this. So we know that cotangent of theta is equal to cosine of theta over sine of theta. And we know that cotangent is equal to 4 over 3. And we know that sine is equal to 3 over 5. Over 5. Okay. So because of this, we can multiply both sides by 3 over 5 to get rid of this fraction, right? Doing that, we're going to end up with 4 over 3 times 3 over 5 is equal to cosine of theta. So we notice the 3's cancel, and that cosine of theta is equal to 4 over 5. Alright, so how the hell is this going to help us? Well, we know that cosine is equal to the adjacent leg divided by the hypotenuse. And we know the hypotenuse is 1. So that means the adjacent leg must just be 4 over 5. And that's all there is to it. So you might be looking at this and you're like, okay, how did I know to use the cosine over sine? And how did I do this and how did I do that? Honestly, the best answer I have to that question is through practice. None of this stuff comes natural to anyone. None of it does. It just takes practice. Recognizing that cosine was going to be, or is equal to adjacent over hypotenuse, and the fact that the hypotenuse is 1, using those two facts, I was able to see this route. So like I said, it just takes practice. Having said that, because it does take practice, I would like you all to look at the last couple pages of these notes. Again, this is section 1.3. There are several examples in the notes that I didn't go over. So please, by all means, take a look at them, kind of digest them. If you have any questions, feel free to shoot me an email. And keep an eye out. I will be releasing an email with office hours this week. Having said all that, have a good one, guys.